All right, welcome to our discussion on the evolution of the IP protocol. This is kind of a free-form discussion just to kind of browse through some of the issues along the IP protocol and its evolution. Hold on a minute. Hey. All right, I'm back. Sorry to delay there, but we're having some technical difficulties, so I'm back at it. So we're going to go ahead and continue on. So I'm going to talk about the IP protocol, and I have a couple of things to show you, so I'll do that now. And I just want to make sure you can see this. So hopefully you can see this.
Yes.
How's it look, Stephen? Wait, that didn't turn out so good. There you go. How's that? But it doesn't show in presentation mode very well. I'll have to fix that. That's okay. Whatever. All right. I want to skip all this stuff in here, and I want to jump down to something very important. This right here. You see this one? So the Internet Protocol started literally as a large community project of research scientists. And the IP protocol really came out as an initial protocol. And a bunch of propeller heads that used to work for Xerox and a couple of other companies, IBM, a few others, and they were getting contracts for the federal government under the DARPA project and a couple of other projects. And they thought, well, we really need to create a better protocol for communicating things. We need to envision it to be bigger and have a process for standardizing. So they created a structure for doing so. And well, I don't want to get into the history of all that because it's long and boring, but the important point is what it's become. And so what you're looking at right here in front of you are the standards organizations that kind of govern the IP protocol. Who just joined us? Let me see. Oh, I don't see anybody that joined us. All right, maybe it was Fred. Anyway, so this is the standard organizations that currently govern the internet. So there's this organization called the ISOC, the Internet Society, and they have a board, an architecture board, the IAB. And then underneath that IAB are research steering groups and the Internet Engineering Steering Group. And they have these working groups and research groups that develop protocols, that develop standards, come up with stuff. And they go through a process. And that process ultimately ends up producing standards that govern the IP protocol stack. Now, this gets kind of convoluted because there's more than one organization involved here. You have, going back to this slide, you have the ISOC, the IAB, the IETF, but you also have the Internet Engineering, the Institute of Electronic Engineers, IEEE. And IEEE is probably the most well-defined engineering organization in the world. And this is really what used to set the United States apart from other countries. But IEEE is now an international organization. There are a lot of engineers throughout, there's 160 countries that participate, and they build and create standards for electronics and other stuff. And they're very much involved in the evolution of modern technology, specifically IP networks. Another organization is called the ISO, or the International Standards Organization. Years ago, they created a model called the OSI model, and the OSI model created a layered approach of communications. Now, the OSI model and the IP protocol are related but not the same. So the IP protocol was designed to work at one of the layers of the OSI model. But what eventually happened is this IP protocol stack of protocols, meaning it's more than one protocol. The stack of protocols created this equivalent model of the OSI model. So basically, the OSI model was theory, and the IP protocol stack was actually implementation. Now, many organizations have come up with ways to create this OSI model stack. Here's a closer look at it. So this is the OSI model. Now, when the ISO originally created this, the ISO actually created a protocol that would work, but nobody ever used it. All these manufacturers and vendors were creating some, and I think I have a slide somewhere in here that goes over that tells you some of the different vendors. Let me see if I do. If I do, I do. Maybe I don't. Yeah, here it is. So over here on the left-hand side, you'll see layer 7 through 1. That's the OSI model layer numbers. Physical layer, data link layer, network layer, transport layer, presentation session, application layer. So you have all those layers over there on the left. And what you see over here to the right are the instantiations or the instances of different manufacturers. So Novell, which was a company that ruled the universe several years ago, this company had their own protocols that fit that stack or the model. Apple created their own stack. Microsoft created their own stack, but Microsoft's was so ridiculously bad that we no longer list it. And then ISO had their own version, which nobody ever used. And then you have TCPIP. Now, TCPIP, which is the Internet Protocol, which is governed by that board, the IAB that I just showed you, that has become the defunct standard. So most people nowadays use computing that is the TCP/IP standard, whether you're on a Microsoft machine, a Unix machine, Apple, it doesn't matter, your mobile phone, your Android, whatever it is, we're always in this stack. So networking students 10 years ago had this horribly complex world of protocols all over the place. And networking students 20 years ago had it really bad because they didn't even have a model. So now we have a model, we have a standard, we have a governing body that organizes this, and pretty much the entire universe has fallen into this TCP/IP arena. And so that's why it's important for us to talk about that from that perspective. Now, so you have these organizations. Every one of these organizations you see here have some influence over standards that govern communication on a network. Now, they may govern logical communications between two devices, or they may govern more of a physical issue. So the IEEE, the EIA, the TIA, the International Telecommunications Union, all of these are more of the physical. They're dealing with the electronic components that connect things together and making sure they work on IP networks. But the real one that we want to deal with is the IETF. So what I'm going to do now is I'm going to open up this web browser, and if you want to join me, you're welcome to. But I'm going to go to IETF.org. This is called the Internet Engineering Task Force, and their website hasn't changed in I don't know how long. But the IETF is pretty much the one you need to know about. They're the ones that govern the development and the creation of new IP standards. So what you're looking at here is their main website, and you can see all these different events they have coming out. You can register for and attempt to, I don't know, I've never tried it. Yeah, here, if you want to try to register for one of their events, you can try to go to that. But, you know, they do require that you be a member of something. So, and usually they remind, usually these are meant for IEEE geeks. So if you were to graduate from Mount San Jacinto College and you were to head off to a 4-year school and specifically get a degree in engineering at an IEEE worthy school, then you would get accepted into and become a member of IEEE, and then you could potentially start to participate and be a member of one of these boards or these working groups that would ultimately attend one of these meetings. And you can have these really lively, fun debates about whether or not we're going to allow automatic addressing in the IP version 6 protocol stack, you know, or stuff like that. So, but I won't bore you with the details, although it is really boring. You can look at their audio archives if you wanted to see how boring it really is. But the point I want to point out to you is over here to the right where it says InternetDrafts and RFCs. Now, RFCs are really the way it happens. So what happens is a bunch of people will get together in one of these working groups. In fact, why don't we just take a look at a couple of their working groups? They may actually have. So I'm going to go to InternetDrafts, and I'm going to look at their. Let me see if I can find a couple of. Here's a couple of internet working groups, right? So I'm under working groups, and I'm looking at applications or internet. So I'm going to go under internet. So here's a working group, and let's take. So here's the IP version 4 on dynamic host configuration. Here's one that may interest all of you, home networking. So there is a working group on home networking. And the home networking working group basically creates these drafts. And this is what you see as a draft. Now, as they work, is it not showing on your screen, Stephen?
No, it's not.
What? Oh, man, that's because I'm doing it wrong, because I'm dumb. I will fix that. How about that? Does that work? All right. All right.
Sean just joined.
Hey, Sean, how are you? You made it.
Yeah, finally.
Yeah, you missed all the fun we were having getting WebEx to work. It was all broken. And we're still obviously stumbling because I wasn't sharing my desktop as I was clicking on stuff and showing people things.
It's hard with multiple desktops.
Yeah, that was the problem. I had the web browser over on the other desktop, and I forgot. So anyway, we're talking about how the IP protocol, how things evolve in the IP world, and I'm trying to stay away from a long, boring historical discussion. I'm talking about the way it actually happens right now, and so. I'm now looking at the IETF. So I want to go back because nobody saw it. The main website you want to go is IETF.org. This is the organization that governs the IP standard. And I say IP, but really it's the TCPIP Protocol stack and all the stuff that goes along with that. So it's the TCPIP Protocol stack. And if you remember, I showed you what that stack looked like when we were here. It's all of these protocols that are part of the TCPIP protocol stack. So all of these protocols that make up that stack are what the IEEE is interested in, or the IETF is interested in, I should say. So basically, there are these working groups, and I was just showing you a place where we could look at some of these working groups. So I'm going to go to InternetDrafts, and over on the left-hand side, you can see some of these working groups. And so we were poking fun at the HomeNet working group called Home Networking. So HomeNet is a group of geeks that get together, and they talk about home networking. And eventually, they come up with these drafts. So, gee, all right, I have this really cool one called the Grazed and Lightweight Open Protocol, Gallop. And they basically created this draft. And so you're looking here at the draft of the Gallop standard. And this is an active internet standard. And so basically what happens is you got a bunch of geeks over here, all listed on the right-hand side. Most of them are, notice, faculty members at Copernicus University. So on July 15th of 2013, they released a draft of their discussions. And if you look through this, you can read their draft. And I'm not looking at the whole document, but you can look at it. And this is identifying their protocol that they've created called Gallop. So let's read it just real quick. The main goal for the protocol is to provide fast and reliable communication between mobile devices and personal computer via Bluetooth with minimal data size needed to realize full functionality of the project. All right, so this is an enhancement on Bluetooth for local mobile devices to talk to personal computer server software. Obviously, this is needed, right? Everybody wants this. I mean, when I walk into my house, wouldn't it be cool if suddenly my phone were to sync up with everything, right? And my messages would all sync, my voicemail would all sync, my whatever I'm interested in watching, my YouTube channels I'm following, that would sync with my TV or my computer or whatnot. So this is a big project. A lot of people are working on this kind of thing, so I make fun of it, but in reality, it's important. So this is their protocol idea, and right now it's just in a draft, meaning they're just working on it. So nothing's happened with it yet. Now, when they get really serious, really serious, it then moves from draft and becomes a request for comment. Now, a request for comment is a big deal. In fact, I'll go to back over to here. We'll go to RFC pages, and we can go to the RFC search pages. And here is a way you can search for all of the RFCs out there, right? And so basically what happens is once you create an RFC, a request for comment, you get assigned an RFC number. And at that point, it goes through several renditions. So the request for comment will start at one phase, and then it'll move down through various phases until it finally becomes a accepted standard and is ratified to be included in the TCPIP protocol stack. So for example, I could type HTTP. That's a protocol we all use. So here are all of the RFCs that were ever created that have the word HTTP in it, right? Hypertext Transfer Protocol. So you might have heard that there was this guy named Berners-Lee, Tim Berners-Lee, who invented the internet. No, it wasn't Al Gore. It was this guy, right? And why do we say that he invented the internet? Well, take a look at it. The first RFC that was created on HTTP was in May of 1996, and it was RFC 1945. So if I take a look at that, you can see that. Now, this one is informational only, meaning that it is defunct, meaning it's been replaced by a more modern RFC. So, but what I want to point out is I'm going to go ahead and go to this. This is the original RFC launched by Tim Berners-Lee at MIT, some guy from UC Irvine, and another buddy at MIT in May of 1996. And if you really want to have an enormously fun reading effort, read this RFC from beginning to end. And what you will learn during this RFC is what the process is for HTTP communication between a web browser and a web server. This RFC changed the world as we know it, right? You're looking at it right here. Now, this RFC didn't stick around. It got superseded. It got replaced by other RFCs that became more accepted, all right, if you will, or had more recent versions. And as you look down here, you'll see that HTTP has been a constant discussion for years, right? And as you go through here, you'll see there's been different versions. This was HTTP 1.0. There's HTTP 1.1. Right? And notice here, RFC 2616, this one obsoleted RFC 2068. It obsoleted all these RFCs, right? And so you can see over here to the left, there's different phases. There's the informational phase, there's a proposed standard phase, there's experimental phase, draft standard, right? Draft standard, and then you have ones that are just best practice, right? It's not a standard, it's a practice. But draft standard is usually one we live by, right? So I'm looking up here, and this is an RFC that has made its way all the way through to draft standard. And so HTTP 1.1 is the one that we still pretty much use, actually. HTTP 1.1 is the modern HTTP protocol that we use on the internet. So I'm actually showing you right now in a web browser, and that web browser is using this protocol to view HTTP traffic. Now, if I click View Page Source, a lot of times you'll see I'm viewing the source of this web page, and up at the top, sometimes it says it, but in this case it doesn't. A lot of times you'll see reference to the HTTP 1.1 protocol up there, but it doesn't. So anyway, there you go. But I could show you something kind of cool. No, I won't do that. I won't distract you with cool stuff. But we'll get into how HTTP works at another point. But anyway, here you go. That's the RFC process, and I wanted to make sure everybody understood that. Any questions about that? Anybody have any comments or questions about RFCs and how that works? This is when you tell me if somebody chats a question, Steve. If not, then forget it. We'll move on. All right. Okay, so there we go. So let's go ahead and take a look at, I just typed IP, and look at all the ones that, there's a lot of ones that reference the word IP, so there's just too many to count, but you get the idea. So this is the RFC process. Let's go back to my slide deck and continue on our discussion. All right, now, TCPIP developed out of this very complicated process that started at ARPANET, and it just started growing and blossoming, and now it's become this default standard. But here's the current protocol stack. So, and most of these, by the way, you can gain access to right on your computer, right? So, in fact, I'll show you my computer. I'm opening up my network sharing center and on my Windows computer. So you're going to be seeing this in a minute. So here's the protocol stack. You have the application layer protocols. You have the transport layer. You have the internet layer, and you have the network access layer. Now this roughly corresponds with the OSI model, layers 7 through 1. If you remember, we talked about that. Here's the OSI model. So this is layer 1 at the bottom, layer 2, layer 3, layer 4, layer 5, layer 6, layer 7. The OSI model is simply theoretical only. The OSI model proves to you a model of layered encapsulated communications. It actually doesn't exist in real life, and nobody actually follows it anymore. In fact, the proof of that is the fact that the OSI, the one that we all follow is the TCPIP protocol stack. The TCPIP protocol stack loosely follows the OSI model requirements. So if you look down here, you'll see network access layer, that handles the physical and data link layer of the OSI model. The internet layer handles the network layer of the OSI model. The transport layer handles the transport layer of the OSI model. And the application layers handle the top 3 layers of the OSI model: application, presentation, session layer. Those are those protocols. Every one of these protocols is included in the TCPIP protocol stack. So going back to my network card. So I'm going to take a look at my Ethernet. I'm looking at my Ethernet network card here. Do you see that? I'm going to go to Properties. And in this Properties windows, you're going to see a couple of things. So first off, you're going to see that I have my adapter up here. Do you see the adapter? Notice that my adapter says the word Ethernet in it. So this gets confusing, but it's important to understand. Every manufacturer of a network card who wants to write their network card to work with an operating system must write that network card with a wrapper or a driver set that will work with the operating system. In the Microsoft world, that driver or wrapper set is called NDIS, network driver interface specification. Every network card that you add into a Windows computer will be written with a driver that supports the NDIS specification. So what you're looking at here is a network driver that supports NDIS. NDIS wraps the Ethernet protocol. So basically, whenever our TCPIP protocol stack, which you see here, which I have installed right here on my Ethernet properties, that has been bundled with, or the proper term is bound to, a NDIS driver that supports Ethernet. Now, Ethernet is therefore the protocol that works at the data link layer and allows for the transformation into physical communication over electromagnetic signal. So if my network card is going to send voltage out on a network wire, basically what's happening here is the network card is handling the Ethernet portion, the data link layer portion, and converting that to physical communication. You then bind a protocol to that NDIS card. And so what you're looking at here, I have multiple protocols listed in here. This can get a little bit confusing to people. The one that we use most often is the one that's called Internet Protocol version 4 or TCPIP version 4. This is the protocol stack that I need to communicate on the internet. Now, I have multiple protocols on here. I have TCPIP version 6. So Windows comes by default with two protocol stacks, IPv4 and IPv6. Both of those are the same kind of thing. They both have a stack of functions that they deliver for your computer. These other ones are Microsoft-specific services that are bound to your network cards. Those services can also use your network card. Some of them have to do with printing. Some of them have to do with discovering other applications on the network, such as files and printers and things like that. The ones you need to worry about are these last two ones. So back to this slide. The network access layer is handled by an interface driver that is wrapped with a protocol such as NDIS, or Network Driver Interface Specification, and that is what handles this layer down here. We then move up into protocols that are actually supported by the Internet Protocol. Now, if I open up a command prompt on my computer, I can gain access to most of these protocols right from within the command prompt. The first one is pretty important. It's called ARP, A-R-P. So if I type ARP, you will get a list of things in here. ARP allows you to resolve Internet Protocol IP addresses or Internet layer or network layer addresses with physical layer addresses or MAC addresses. So if you type ipconfig/all, you can see my TCP/IP settings on my computer. So that was ipconfig /all. And what you're looking at here are my IP configuration on my computer. So you can see here I have an IP address 192.168.1.3. That is my logical IP address or my internet layer IP. And then you're seeing here the MAC address or the physical address right here. That one that says 5CF9DDE0FE01. That's my physical or MAC address. That is the network access layer address, or sometimes referred to as my Ethernet address or MAC address. So if I wanted to talk to a computer such as this IP right here, 192.168.1.1. So I am now pinging that computer. And by the way, when you use the ping command, you are using a protocol called ICMP. Do you see that right here under Internet Layer? There's a protocol called ICMP. The way you gain access to the ICMP protocol is you use the ping command. So when I type ping in an IP address, it basically sends out an ICMP echo request, and I get an echo reply back from the computer, and therefore I know that IP is working properly. Now, when I sent that ping to the IP address, my computer has no idea what the IP address's physical Ethernet MAC address is. However, I rely on the ARP protocol, address resolution protocol, to find it out for me. So if I type ARP-A, you will see that my computer has went out and found a whole bunch of MAC addresses. And if I look in here, you will see this one right here. I'll mark that real quick. This one right here, you can see it went out and found a MAC address for the machine 192.168.1.1. So my machine now has the network access layer address, or the physical or MAC address of that machine, and I know the logical IP address 192.168.1.1. Now, it's not good enough just to talk at the internet layer and the access layer, because we're talking about layered communication. So if I wanted to talk to a web browser, like let's say I wanted to go to www.msjc.edu. So I want to go to the college's website. I just established a communication with the college's web server using the HTTP protocol. Going back to my diagram here, notice that HTTP is up here, right? You didn't see it, but I actually had to type in the browser HTTP, meaning I'm using the HTTP protocol to interface with the TCPIP protocol stack and send an HTTP 1.1 GET request to this web server. And so that's what exactly happened here. HTTP protocol communicated to the web server. Now, it didn't talk straight to the IP protocol. The HTTP protocol talked straight to one of these protocols at the transport layer, in this case TCP. How do I know that? Well, I can go here and I can type a command called Netstat. And I have to get a little bit more trick with Netstat than just this, but we'll see how it goes here. I think I can actually have Netstat resolved by name. That's a little easier for us. Give me a minute. -F, I think, is the command. So I'm going to do netstat-f, and there we go. So this is showing you all of our communication that our machine has established with the transport layer to machines. So what you're seeing here is I have these established communications with other machines. You see all that up here? So I have one with, God, I'm connected with a whole bunch of machines all over the place here. Who the heck am I talking to? Oh, I went to Google. That's my problem. They do so much advertising and marketing, they just kill you. All right, there you go, right there. Take a look at that. See, my machine is communicating to msjc.edu. Do you see that? And I've established a communication on the HTTP port, right? Now, so my machine, coming from some obscure port number, is talking to msjc.edu on the HTTP port. Now, what is the HTTP port? Well, let's take a look at this, and what I'm going to do is I'm going to make it display numbers instead of names. So I'm going to type -F-N, and there we go. So I'm going to scroll back up here, and there it is. I'm talking to msjc.edu, which is 207.233. That's the IP address of Mount San Jacinto College's website. And notice the colon, it's port 80. So my computer right now is talking to the college on port 80. So I am using the HTTP protocol right here. to talk to the TCP port 80 on the IP address of 207.233.7.9. And in order to get out there, I had to resolve the MAC address of my router in order to send that communication out. So this is how the protocol stack works. Now, it's not that easy, though. Just when you thought it was getting complicated, it's not that easy. Some of you may have been pretty smart to figure out, well, hey, wait a minute. How did it know to go msjc.edu, the name, to the IP address 207.233.7.9? How did it know to do that? Well, looking over here, there is a name system called DNS, Domain Name System. And DNS allows me to resolve names to IP. The utility that we use for that is called NSLOOKUP. And if I simply type a domain name in, like www.msjc.edu, it will return and resolve for me an IP address. So as you see here, I resolved the domain name msjc.edu to the IP address 207.233.7.9. So that is where the DNS protocol kicks in, right? Now, I don't have to HTTP. I could use any one of these other protocols up here. I could send an email message. I could transfer a file. All these types of things. So there's many different protocols up here that we can use, right? The point is that of all of these applications, that all these variety of layers in this entire stack are all governed by the IETF. So every one of these has standards that have been created to govern each one of these protocols. And every once in a while, one will become a really hot topic, right? Like email, that's always a big one, right? Because we use email. HTTP is a big one because we browse the web all the time. DNS is a big one, or it was for a while, but it's not anymore because we kind of figured that out. Right now, a big hot one is the IP itself because IP version 4 is running out of addresses. So the Internet Society actually gave control over the registration of actual IP addresses with public entities to an agency. And let's go ahead and take a look at them. So this is the agency that was given the ability to register IP addresses for the Internet Society in North America. There's other ones outside of North America. But this organization is responsible for assigning out and carving out IP version 4 addresses to those that request them. But look over here to the right. What does this tell you? The ARIN IPv4 countdown plan. Wow, what does that mean? Well, it basically means that we're running out of IP addresses. So we only have the equivalent of one Class B or roughly 2 Class B addresses available. And they have a countdown plan that's in 4 phases. So phase 4 means that we have no more addresses left, right? So in phase 4, it's like, goodbye, no more IP addresses. So that creates a problem, right? If IP version 4 is running out of addresses, we got to deal with that. Consequently, they've created, through the draft process, through the RFC standards process, through the ratified standard process, they have created a new IP protocol called IP version 6. So IPv6 is the replacement for, or the augmentation to, the current TCPIP protocol stack. So as our society evolves and changes, as we get more mobile devices, as we get whatever crazy thing's going to come out down the road, we have created a protocol stack and communication process that can adopt itself through a standards process that works its way up through the engineering community throughout the world, And that process has produced this protocol stack that allows for our types of communication. It allows for WebEx calls and video to be streamed like we're doing now. It allows for my cell phone to receive and send messages. All of those have been governed by one or more RFCs that have been created through the IETF. All right, that is a rundown of the IP protocol standards process and why we have RFCs. By the way, here are a couple of the big hitter RFCs that are listed in the slide deck, just to give you an idea of them, and that gives you an idea of what they are. And somebody asked me, will I make the slide deck available? Yes, I will. All right, that's basically all I wanted to cover today. I'd like to open it up to questions at this point, and I hope I have one. I really want a question. Please, question. Question, please.
Can we find a picture of the protocol suite and communication on the Cisco website?
Yes, that OSI Model Stack is in Chapter 3.
Okay, thank you.
Absolutely. And most of those slide pictures are that came from your curriculum, by the way.
Okay, good.
But there you go.
So there's not going to be any more IPv4. It's all going to be IPv6?
Well, it's going to be a long time coming.
Oh.
IPv4 will be around for a long time. IPv6 is in use today. In fact, I can go to
Hey, Guy, can you hear me?
yeah.
Hey, it's Sean. Hey, I was wondering, did you ever find out if we can get offline access to the Cisco for Chapters 3 and 4 for any of your studying to be doing offline?
No, you can't. I can download it, but I'm not allowed to give it to you. I did download it, though, and I'm making it available on an internal college web server, and I will post it in Blackboard as soon as I get that up.
Thank you.
And that may make it a lot easier for you to grab it and print it or do whatever you want with it. But I'm not allowed to disseminate it to you on a flash drive or something.
Okay.
Now, just real quick about this IP version protocol thing. Ping ipv6.guyreams.com. And there we go. Look at that. So I'm only using IP version 4 over here, but I have an IP version 6 address out on the internet. And there's my IPv6 address. Do you see it? So that's the IPv6 address. Now, you can get your own IP version 6 address if you want it, by the way. So just for fun, if you want to qualify as major geek status, the website you want to go to is called Hurricane Electric. If you go to Hurricane Electric, you can sign up for an account, and you can get your own account, and they will give you a free IP version 6 block, and they will set you up with a tunnel broker. So you can actually have your home machine create a tunnel to the IP version 6 network, and you can communicate and browse websites in the IPv6 network. And by the way, there are many organizations already on the IPv6 space. So here's the IPv6 everywhere map, and everybody's connecting into it to create the IPv6 network. And most of your big organizations like Google and Yahoo and you know, you name it, Amazon, eBay, they all have IPv6 presences now, including me. I'm on there too. But all I have is a place you can ping. I don't even have a website. But if you want to, go to Hurricane Electric and check it out. It's pretty cool. You can watch their videos, and they'll teach you how to do it. I may actually do a video on how to set up an IPv6 tunnel broker as a fun deal, but I haven't got to that yet. Cool. It's pretty cool. It's pretty fun. I have a tunnel broker running on my home machine, so it's kind of cool. You can also buy a routing device that you can plug into your house that replaces your router, and it will actually bridge you onto the IPv6 network. And what's really cool about it, you know how you're always fighting your ISP for a static IP and all that? Mm-hmm. Well, with the tunnel broker device, you have literally 65 million static IPs. So if you want a static IP to run your web server on, your mail server on, whatever the heck, then get a tunnel broker connection to Hurricane Electric, and now they will give you a /48 prefix right here. And I won't tell you how much a /48 is, but that's your homework. Go online and research how big a /48 IPv6 network is. And that's how many static. What's a /48 IPv6 network? You can figure that out on your own. But it's big, right? And so they're giving those away for free. That's how many IP addresses are possible in the IPv6 space. So, any other questions for me? All right, I got a good question from Sean. I got a good question from Roberta. Fred, Diane, any questions? All right, long, silent, pregnant pause. Okay, so just to point out, on the Cisco curriculum, Roberta asked the question earlier, focus on the packet tracer assignments, right? Focus on those. I will have some videos coming out next week that go over how to do the chapter 3 and 4 ones. They're a little bit more difficult. And there you go. Thanks for joining. Sorry for all the difficulty and challenges, Sean.
Not a problem. I got in here. Just make sure we get it the next time. It should,
no.
You said you're supposed to be getting a registration email, so there was no email that came back in any way.
Yeah, we figured that out. I couldn't figure out why nobody was joining, and I figured it out. Roberta was the one that alerted to me. She actually figured out that if you went back in and click on re-email me, it actually sent it out the second time. But I don't know what the problem is, so I got to figure it out.
Okay.
Anyway, thanks for joining, and I'm going to be sending out a schedule of some more events next week, and thank you very much.
Thank you.
Thank you.
Have a good weekend.